In this video of Chapter 5, which is about the periodic table, we're going to focus on periodic trends. And I did include ionization energy as a part of this trend because it is a trend. So let's take a look. So there's actually three trends we're going to look at. Atomic radius, so that's the size of the atom. The metallic or non-metallic nature of an element, and then ionization energy. So we're going to look at those three. So and at the very end of the video on the periodic table, like you'll have for the exam, I'm going to write all the trends on one periodic table. So periodic trends. So the first one is the atomic radius, and I just mentioned it, but I like to say that what we're talking about is the size of the atom. And so in general, as you can see in this illustration, which only has representative elements, the trend across the transition elements is generally the same, but has some exceptions and is not as quite dramatic. But if we're looking here at the representative elements, the radius gets smaller as you go from left to right across a period. So the period is the rows. If we're looking at a group, so that's the columns, it gets smaller as you go up. So in general, in the upper right-hand corner of the periodic table are the smallest atoms, and in the lower left-hand corner are the largest atoms, just as a general idea. Okay, so it gets smaller across and smaller up or bigger down. Like you could do it either way. I'm not going to ask you to tell me which atom is the smallest, but I do want you to understand that the smaller atoms are in the upper right-hand corner of the periodic table and the larger atoms are in the lower left hand. We also want to understand just things like as you go down the periodic table, the bottom of the periodic table has larger atoms than the top of the periodic table. So generalizations like that. Now here's the explanation of atomic size, which I think part of it's really easy and then part of it you have to stretch a little bit. So as you go on, if you look at number 1 here, like why, this is the one you have to think about. It says, why would it decrease as you go from left to right? Why would it get smaller? Because in theory, as we go across a row or across a period, each new element is getting another electron. So you would think, well, why isn't the volume getting larger of the atom? But it not only is it getting an electron, it's the nucleus is also adding a proton. So as you go across, the nuclear charge is increasing. Now, why it shrinks as the nuclear charge increases is that in a period, all of the electrons are in the same energy level. So if you're in period 2, all of the electrons in period 2 have energy level 2, and so that whole level gets pulled in by the increase in nuclear charge. So it has to do with why it's getting smaller as you go across. There's 2 factors. One is that the nuclear charge is increasing, and then 2, which is also important, they have to be together, is that the outer electrons are all in the same level, and that level is being pulled closer to the nucleus. And we talked about energy levels in the previous chapter. Now, why do they get smaller as you go up or larger as you go down? Well, as you go, we'll think about going down the periodic table. As you go down the periodic table, you are adding energy levels to the atom, and so it's like you're adding layers. I know it's not layers, but in my imagination, you're adding electrons to new layers, and so as you go down a group, it gets smaller. Then you can think the opposite. If you're at the top of the periodic table, there's fewer energy levels, and so the atom is going to be smaller. So that's one trend, atomic size. And at the end, I'll put all of them on one periodic table where you can kind of see. Here is a practice, and I put a periodic table in here. So let's draw the trend on this one. So just in general, as we go across left to right, the atom gets smaller. And as we go up, and I'll just put it over here just so it's out of the way, but I could put it in any of the groups. Okay, so that's our general trend. So when it says based on general trends, predict which is has a smaller radius. Okay, sodium, which is here. Oops, I don't want it to go away. I want to be able to see it. Sodium. Let me get a shearer. I want to be able to see my letter. Sodium, still not sheer, huh? And potassium. Okay, so we know, what does it want us to do? Predict which is smaller. So we know as it goes up, it gets smaller. So then sodium would be smaller than potassium. This time I'm just going to circle it so I can see through. So calcium, so that's this one. And then nickel, which is further over. So we know even though the transition metals do not have as much of a pattern, we know in general as you go from left to right that the size is going to decrease. So if they want to know the smaller one, we would predict that nickel would be smaller than calcium. I'm not asking you to memorize any kind of exceptions. I want you to know the general trends and then to be able to reason with that general trend what you expect to happen. If at some point in your educational career you have to start learning exceptions, then you can add it into your trends. Many trends have exceptions to the trend, but trends do help us predict and understand things. So we'll try to use them. All right, so what's the next trend? The next trend has to do with metals, nonmetals, and semimetals. And so before we do that, I want to show you on the periodic table, we can identify these three categories. So you see here there's a stair-step line right here. And that stair-step line divides the two big categories. On the left, these are metals, except for hydrogen, which is a non-metal. Oops, I touched the screen in it. I don't know if you could see it, but on mine it did something. So I'm just going to outline it. These are all metals. Here, I got to be careful once I get around there. I'm going to leave that open for a second, and you'll see why. And these are all, because they're taken out of the metals, those are all metals. And then we have the non-metals. The non-metals are on the right. Oop, I didn't want red there. Sorry, I can get red, but I don't want that thick pen. And so the non-metals, and you'll notice I'm leaving some space maybe here, and then this hydrogen is also a non-metal. And now we have the semi-metals. Okay, so semi-metals are also known as metalloids. And metalloids are along the, or semi-metals, are along the stair-step line. So they are, I'm just going to put a little arrow, and then I'm going to show you, because it's not all of them. Let me write semi-metal. Your book uses semi-metal. I'm more used to metalloids, but I'm going to be consistent with your book so that we can... I just want to be consistent with your book. Okay, so semi-metals include boron. Now, not aluminum, because aluminum has properties of a metal. But then it goes on either side. So silicon, germanium, arsenic, antimony, and then tellurium here, polonium. And your book includes astatine. Some books don't, and it's okay. Again, I'm going to go with what your book is doing. So those are the semimetals. So they go on either side of the stair-step line except for aluminum. So aluminum would be apart. So then my metals come like this. And don't get too tied up about the ones on the very bottom of the periodic table. Most of those are just radioactive, don't exist very long. So we've got these three categories. We've got nonmetals, which I have in red. They're the middle size category. In purple, I have the metals. So the majority of elements are metals. And then of those three categories, the smallest one would be the semimetals. So this is another classification. In the previous video, we labeled representative elements, transition elements, intertransition elements. We also labeled the four groups, the alkali metals, alkaline earth metals, halogens, and noble gases. So you can review that. This is in addition to that. So this is another broad classification that we will use when we talk about bonding. Now, you might already be able to see the trend then, because one of the trends is in metallic properties. So let's look. So the trend in metallic character, it says, recall, metals are on the left and nonmetals are on the right. So metallic character, as you go across from left to right, they're going to become less metallic. And as you go up a group, they're going to become less metallic. And here is a really great takeaway. The trend is similar to the atomic radius. So that means the smaller atoms are in general non-metallic. The larger atoms have more metallic characteristics. I'll write that down. And then the semi-metals, they actually have, why did I put atomics? Because I was thinking of metallic. Sorry, let me write that correct, smaller atoms. The semi-metals have some characteristics that are from both. So we have this type of relationship. Now, our goal is going to, again, we won't necessarily know what is the most metallic. We're just trying to predict trends. So let's try a question. So it says, based on the trend. Okay, so let's write it. We know as you go from left to right, they're going to become more non-metallic. So less metallic, you could think of. We'll have to see how the question's worded. And then as you go up, they're more non-metallic. All right, so let's find these. Tin or lead. Okay, so here is tin and here is lead. So they're both there in group 4A. And we want to know the question. Let's read the question. I jumped ahead. Which element is more metallic? Okay, so we know as you go up, you're more non-metallic. As you go down, you would be more metallic. So the bigger they are. So lead would be more metallic between those two. Now calcium and sulfur up here. Okay, so what we know is you go from, and we want more metallic. Okay, so as you go from left to right, you become less metallic. And as you go up, you become less metallic. So between calcium and sulfur, calcium would be the more metallic and sulfur would be the less metallic. So the answer would be calcium. And that makes sense because here's my stair-step line, and to the left are metals and the right are nonmetals. So calcium is a metal and sulfur is a nonmetal. Okay, and again, on the last page, I'll put all three trends together. So then our next trend is ionization energy, which if you're following along in the slides, ionization energy is a little further down, but it really is a trend. So I decided to include it in the trend part of the presentation. So ionization energy, you can see here, it's how much energy it takes to remove an electron of an element that's in a gaseous state. And what you'll see is it is the inverse relationship to both metallic characters and size. So in this case, ionization energy increases as you go from left to right. It gets higher across a period, and it increases as you go up. So on this periodic table then over here, this has the highest ionization energy, and this has the lowest ionization energy. I'm just putting IE for ionization energy. Now, I always like to kind of, when I'm talking about ionization energy and its trend, I like to relate it to the size of an atom because in my mind, it makes some sense. So in the upper corner here, these are small atoms. Right? These non-metals are the smallest, and down here are the largest. So I want you to think about it because small atoms, what it means is the outside electrons are closer to the nucleus because it's small. And so the distance between the positive nucleus and the outside electron is less than if you go to a large atom. Imagine in your head a big atom. That distance between the nucleus and the outside electron is greater. Now, ionization energy is how much energy it takes to take away that one electron. So if you think about it, if your electron's closer to the nucleus, remember positive and negative charge, the closer they get, the stronger the attractive force. So there's got to be more attractive force for that electron to the nucleus in small atoms. And in large atoms, the attraction is less. And so you have a lower ionization energy. And in my mind, I'm thinking, okay, here's a nucleus and here's my atom. That distance is less. There's greater attraction. It takes more energy to remove that electron. Down here, I have a nucleus, and then it's a bigger atom. This distance is greater because this is the plus, the electron is the minus. And so this electron, it is easier. It has a low ionization energy. It takes less energy to remove the electron. So let's see if we can predict about the ionization energies. Now, general trends. Now, for some reason, I didn't put the periodic table. But let me show you what I do when I don't have a periodic table and I want to visualize it. I just draw a messy one. I'm just wanting a trend, right? And I know that ionization energy increases this way. And I'm just putting IE for ionization energy. And ionization energy increases this way. So I have lithium or I have sodium. They're both over here on the hydrogens up here. And then I have lithium and I have sodium. So what am I trying to answer? I want the higher ionization energy. These are in the same, so these are going to be in the same group. And we know in the group, the ionization energy increases as you go up. So lithium would have a higher ionization energy than sodium. It's also smaller. Then we have oxygen and fluorine, and oxygen is over here somewhere on 6A, and fluorine is 7A, somewhere around here. So these are in the same row, and we know that ionization increases, energy increases as you go from left to right. So in this case, the fluorine would have the higher ionization energy based on the question. All right, so let me take a periodic table and write all the trends. And the idea with all of this is that you'll know the trends and be able to answer questions when comparing two atoms. You'll be able to decide which has higher or lower, whichever one, depending on what trend you're talking. So when we're talking about the size, if I go across left to right, my pen is sometimes decreases. Sorry. And then as you go up, it decreases. This might not have been the perfect color. I'll choose a darker color next time. So atomic radius decreases as you go across and up. So the smallest elements are in the upper right-hand corner. Let me choose a darker color. So also along this same line, so we did atomic radius. We also did metallic properties. So metallic properties decrease as the atom gets smaller. So the radius and the metallic properties have a similar trend. And then the last trend is ionization energy. And ionization energy is the opposite. It has an inverse relationship with these. And ionization energy increases. I'm going to write this one up on top so it's not right in the middle of the periodic table. Here we go. Why did I write decreases? I went to go to it increases. I apologize. I was concentrating and I caught my mistake as I went to write the other one. It's the opposite of the radius and the... There we go. It increases. It's the opposite. So, and I can't, it's hard for me to write it now just because of how much writing I have. But what we know here then, down here, these, if I was summarizing it, these are larger, more metallic, and they have a low ionization energy. And if I was summarizing up here, which I'm going to have to kind of write on the side because I have so much writing in that corner, but these would be smaller atoms, less metallic or more non-metallic, however you would like to remember it, and high ionization energy. So trends are important because they can help us predict things and they can help us explain things. So from this section, I want you just to become familiar with these three trends that we can observe on the periodic table.